Welcome to Economics 1723 Capital Markets. This is the online module for the 9th lecture on multifactor models, the APT, that's arbitrage pricing theory, and the SDF, which you should know by now is stochastic discount factor. So we'll go through first arbitrage pricing theory and the general idea of a factor model. Then we'll talk about models with many factors, so-called multifactor models. And finally, we'll try to link back and connect this with the stochastic discount factor approach. So what's a factor model? Well, let's start by running a regression similar to the one that we discussed when we were talking about testing the capital asset pricing model. So we're going to measure all returns on individual stocks I relative to the risk-free rate. So returns are always going to subtract the risk-free rate of interest. We're going to regress the excess return on stock I over the treasury bill onto the excess return on the market over the treasury bill. There'll be an intercept, alpha, a slope, beta, and an error term, epsilon. Now this relationship, this regression, is called the market model or a single index model because there's a single factor, a single variable on the right-hand side which captures the common movement of the market. Now, we can always think about this regression. We can always run this regression. We don't have to assume that the CAPM holds. The connection with the CAPM is that in that model, the theory predicts that the alpha, the intercept, is 0. Okay, so what can we learn from this regression? Well, it's only really useful if we put more structure on. So I'm now going to add an additional assumption. I'm going to make the assumption that the errors in this equation that I just showed you are uncorrelated across stocks. In other words, that the epsilon for stock I and the epsilon for stock J have an expected cross product or covariance of 0 whenever I and J are different stocks. That's saying that the residual risk epsilon in any stock is idiosyncratic. It's unrelated to the residual risk in any other stock. Now, at first you might think that's a fairly innocuous assumption, but it actually turns out to have many implications for returns. It puts a lot of structure on stock returns. Now, what does this structure do for us? Well, a first point is that mean variance analysis for portfolio choice becomes much easier. If you remember, in general, the variance-covariance matrix of asset returns is very large with many, many free parameters, and it's very difficult to estimate those things. Because if you have n stocks, you have n times n plus 1 over 2 elements of that matrix that you have to estimate. Now, in this single factor structure that we're looking at now, the covariance simplifies because since the idiosyncratic risks are uncorrelated, the covariance of the return on I and the return on J is just going to be the product of the two betas times the variance of the market return. In other words, instead of n times n plus 1 over 2 parameters to estimate, we just have n betas and the variance of the market. That's just n plus 1. So it's a much easier problem. But beyond that, we have the so-called arbitrage pricing theory, which says that if many assets are available and the residual risks, the epsilons, are uncorrelated with one another, then we should expect that the alphas, the alpha I intercepts in those regressions, should typically be very small in absolute value. Now I'm going to need to be much more precise about what I mean by that. What does typically very small mean? Well, let's go forward and find out. All right, so here is the arbitrage pricing theory argument, and this dates back to the 1970s, to the work of Steve Ross, who was at Yale back in those days and now is at MIT. Okay, so what we're going to do is consider forming a portfolio of n different assets which are indexed by this letter I. The portfolio return will be linear. It'll have this same linear form as any individual asset return, except that instead of an alpha I, we have alpha P, and then we have beta PM, the beta of the portfolio, and finally the epsilon P, the residual risk of the portfolio. Now, everything's going to aggregate up linearly. So the alpha P is going to be a weighted average of the individual alphas. The beta P with the market is going to be a weighted average of individual stocks betas. And the residual shock will be a weighted average of the individual stocks shocks epsilon. What will the variance of epsilon PT be? Well, this is where we're going to use results from our previous discussion of diversification. The variance of epsilon PT is going to be the sum of squared weights times the variances of the individual shocks. Why? Because there are no covariance terms. We've assumed those covariance terms are all zero. Now this sum is going to shrink rapidly with the number of stocks, provided that no single weight WI is too large. All right. In the benchmark case of diversification with an equally weighted portfolio where the weights are all 1 over n, and where all the stocks have the same idiosyncratic variance, some common number sigma squared, then we get that the variance of the portfolio shock is the variance of the individual shocks divided by n. And this is the same result we discussed a couple of weeks ago when talking about diversification. Now let's think about a so-called diversified portfolio, which is one that has many, many stocks in it with a small enough weight in each one, such that the residual risk, the variance of epsilon PT, is negligible. We will neglect it. We will assume it's basically zero. Then we say that this portfolio is well diversified. And for such a portfolio, we can neglect epsilon PT and write the return as simply RPT minus RF equals alpha P plus beta PM times RMT minus RF. But if you look at this equation and think about it, you realize that we must now have alpha P equals 0. Why is that? Well, suppose not. Suppose that alpha P is not 0. Then there's going to be an arbitrage opportunity. What you can do is form portfolios where you're borrowing at the riskless rate to invest in the portfolio P and or to invest in the market. These portfolios are going to have returns RPT minus RF for this long-short portfolio and RMT minus RF for this one. Now, suppose that you go long 1 unit of P, financing it by borrowing at the riskless rate, and then simultaneously you go short beta PM units of the market, putting the proceeds into the riskless asset. All right. Well, the short beta PM units of the market is going to cancel out this component of the return on the portfolio P. It'll cancel this part out. I'm Xing this out, and you will have a combined portfolio with a return alpha P that is riskless and requires no money down. So it's an arbitrage opportunity. Basically, you can borrow money. You can invest it risklessly and earn alpha P with no money down. Or equivalently, you can put capital in and earn a higher riskless rate than RF. You can get RF plus alpha P. Okay, so this argument, this no arbitrage argument, says that we must have alpha P equal to 0. Now, the non-trivial step, and I'm not going to be able to give you the technical details, is to show that this fact that alpha P is 0 for all well-diversified portfolios has implications for the individual alphas, the alphas on individual stocks, the alpha I's. What it implies is that, quote, almost all individual assets have alpha I very close to 0. The intuition is that you can have a few mispriced assets with non-zero alpha, but if there's too many of those mispriced assets, then you can group them together into a well-diversified portfolio and create an arbitrage opportunity. So the technical result is that as the number of stocks available increases, the average squared alpha is 0. As it goes to 0, the limit is 0. So for a large n, this average squared alpha is going to be very small, and the more stocks are available, the smaller that average squared alpha has to be. Now you don't need to know this formula. I'm just trying to give you the basic idea. All right, now notice what we've done here. We've written down a market model, so there's this market factor, and then we've used an arbitrage argument, and we get exactly the same prediction as the CAPM, namely that alpha is 0. But we've done that without using mean variance analysis, without even needing optimization. We just assumed the absence of arbitrage, which is a much weaker condition. However, we did need a different kind of assumption, a statistical assumption, which is that the residual risk from the market model is uncorrelated across stocks. This residual risk, therefore, is fully diversifiable. It can't be priced. You aren't compensated for a risk that you can diversify away, and so only covariance with the market is rewarded. Now, an important point is that under this approach, the market that we put into that market model can be any broadly diversified portfolio that satisfies the assumption of uncorrelated residual risks. It need not literally be the portfolio of all wealth of investors. And thus, we don't have to worry so much about the fact that we may have mismeasured the market portfolio of total wealth. And this is the so-called Roll critique after Richard Roll, who argued that we really can't measure the composition of the wealth portfolio. But with this arbitrage pricing approach, that problem goes away. All right, so what are the differences between APT and CAPM? CAPM requires mean variance optimality, optimization, and a notion of equilibrium. The arbitrage pricing theory approach requires just the absence of arbitrage. That's much weaker. On the other hand, it does assume a statistical structure on returns, which is a much stronger assumption. And frankly, it's just not the case that all systematic risks can be described by a single factor. There's more than one common shock that's influencing multiple stocks. However, the good news is that the arbitrage pricing theory approach can be generalized to a case where there are multiple factors. So that's what we're going to do next. We're going to talk about multi-factor models. All right, so in practice, no single factor accounts for all the correlations among individual stocks. There are, for example, common shocks to particular industries. Then there are some companies that are particularly cyclical and react to industrial production. There are companies that have a lot of debt, leveraged companies, and they're going to be particularly sensitive to movements in interest rates. There's evidence that value stocks seem to move together, growth stocks seem to move together, and so on and so forth. So to handle this, we generalize the arbitrage pricing theory approach to a multi-factor model. We write down K different portfolios. Capital K is the number of portfolios we need that capture the common influences of capital K underlying sources of risk. And we can run a regression with K different explanatory variables on the right-hand side. These are the excess returns on K different portfolios over the riskless interest rate. Each of them, so stock I, which is here on the left, the excess return on stock I, is an intercept plus K different slope coefficients times these excess returns plus a residual risk. So the new key assumption in this model is that the residual in this regression is uncorrelated across stocks. The prediction of the model then is that alpha I is 0 for almost all stocks, using the same no arbitrage argument that we had before. Now, this isn't going to be very helpful if the number of common factors you need is as large as the number of stocks you have. But if you can explain the returns on a very large number of stocks with just a few common factors, then we actually have a restrictive and useful model. Now, I should mention that there's one alternative way of doing this, which is to measure the common factors directly as shocks with mean 0. For example, we might say they are innovations to interest rates or inflation or industrial production. Things with mean 0, in other words. And we're going to write these mean 0 shocks as F for a factor, and this factor has mean 0. Then the overall mean excess return on any stock is captured here. This is the mean, and then this part has 0 mean. Well, written this way, the prediction of the model looks different. It is that the expected excess return is the sum of the betas times the some unknown free parameters, lambda k, which we call the prices. The price, lambda k is the price of risk of the kth factor. Okay, so because now these things have zero mean, the risk compensation is written here as beta ik times lambda k. If we go back here, why didn't we need that here? Well, here the lambda k is captured in the mean of this traded portfolio, this portfolio of assets RKT. All right, so it got built in automatically. The beta ik lambda k is automatically taken care of by the mean of this thing, leaving nothing over for the alpha. Then the alpha is 0. Okay, so these two approaches, this one here and this one, are two different ways of writing the same thing. Okay, so finally, how does this all connect with the stochastic discount factor approach that we did a few weeks ago? All right, so I'm going to ask you to try to remember the basic formula for the stochastic discount factor, which is that the price of any asset, I, PI, is the expected product of M, the stochastic discount factor, times the payoff on the asset. Now we can divide this equation through by the price of the asset, and then the left-hand side becomes 1. The right-hand side is E times mx over P, and x over P is the gross return on the asset. It's what you get in the future divided by what you pay, so that's the gross return 1 plus Ri on asset I. Now this equation holds for all assets, including the risk-free asset and the market portfolio. 1 equals EM times 1 plus Ri, or 1 plus Rf, or 1 plus Rm. Okay, so Ri, Rf, and Rm are all related through the stochastic discount factor, and the question now is, can we modify this to get the CAPM pricing relation? So I'm going to show you a theorem. Suppose the stochastic discount factor looks like this. It's M equals A minus BRM. In other words, it's linear in the return on the market with a negative slope. Well, the negative slope would make sense in that a high market return means people are wealthy, which means that it's a good time and their marginal utility is low. So we would then expect this relation to look like this. All right, so suppose we have this this relation between M and Rm, then we can show, there's a theorem, that the CAPM beta pricing relation will hold. All right? You can think of this as yet another way to derive the CAPM, just by making this assumption on the SDF. So what we'll do in the next 2 slides is prove this theorem, and then finally we'll interpret to wrap up today's module. Okay, so let's prove the theorem. Now remember that we have this equation. 1 is the expected product of M and any gross return. So let's subtract this from this, then we'll get 0 is the expected product of M and the excess return on I minus RF. And the expectation of a product is the product of the expectations plus the covariance. And that's just a property of covariance. That's true by the definition of covariance. In other words, the mean of the product is the product of the means plus the covariance. Now, if we rearrange these terms, we get that the expected excess return on any asset is minus the covariance of M and Ri divided by the mean of M. This says that the return of an asset depends negatively on its covariance with the stochastic discount factor. That again makes sense because when the stochastic discount factor is high, marginal utility is high, it's a bad time, so an asset that covaries positively with M it has insurance value, and that will justify a low expected return. All right, well next what we're going to do is plug in the assumption of the theorem that M is A minus B times Rm, and that will transform the covariance term into something more familiar. We're going to get that the risk premium on any asset is the slope coefficient B times the covariance of Rm and Ri divided by the mean of M. Okay, so by making this assumption about M, we find that the return of the asset depends on its covariance of the market portfolio. Now, if we divide through by the covariance term, we're going to get that the risk premium on any asset divided by its covariance has to equal B over EM, which is the same for all assets. Okay, so we're learning that for any asset I, the reward to risk ratio is the same and equal to the term on the right-hand side. Now, does this remind you of something? It should. It should remind you of what we came up with when we were doing the beta representation theorem. Okay, so now consider the last equation, both for asset I and for the market portfolio, which we write little m. Don't confuse the little m of the market portfolio with the big M of the stochastic discount factor. But anyway, we have this ratio here for asset I has to be the same as the one for asset M, the market portfolio. And if we rearrange this, in other words, we just multiply through by the covariance, we're going to get that the risk premium on asset I is the covariance of the market divided by the variance of the market times the risk premium on the market. That is, in other words, it's the beta times the expected excess return on the market, and that proves the theorem. So we've just derived the beta pricing relation of the CAPM yet again for the third time, and this time the assumption we made is that the stochastic discount factor is linear in the market return. Okay, to get a positive excess return on the market, we need that relation between the SDF and the market return to be negative. Since the SDF is proportional to marginal utility, the CAPM follows from the assumption that investors' marginal utility declines linearly when the market goes up. And this marginal utility relation is why investors care about market risk. Now finally, pulling it all together, a multi-factor model would follow from the assumption that the SDF is a linear function of K portfolio returns. So a well-known empirical multi-factor model that we're discussing in lecture is the Farmer-French model. That model has the market return, the return on small stocks minus big stocks, or SMB, and the return on stocks with high market-to-book ratios minus low market-to-book ratios, or value minus growth returns. That's called HML. Now that empirical model has these factors being priced, but for that to be the case, these factor returns have to correlate in some way with investors' marginal utility, or else they wouldn't care about these factors. So what equilibrium asset pricing models do is they try to explain why particular factors correlate with marginal utility. And that is where the research effort is today in understanding multi-factor models of asset pricing. So we'll stop there. Thanks for listening.